All right. So next we're going to talk about complex quadratics. Now, I've seen a lot of different ways to do this. I learned one way to do it, which is kind of by trial and error when I first learned it, and then I learned some other ways that are a little more systematic. But they're always none of the ways were exactly straightforward and systematic, and so there's always kind of a little bit of wiggle room in there, a little bit of yeah, little challenge in there, little parts that I always wanted to tweak, and so there's about 4 or 5 ways that I've learned throughout the years. But I observed an elementary teacher, or excuse me, a middle school teacher, one year, and she did this method that I really like, and so we're going to use this procedure here. And if you want to freeze the screen, you can to copy this down at any point. But this is what we just did for simple quadratics, and so if you want a procedure for how to do that, here it is. And so basically, we found numbers. We found numbers that had a product of C and a sum of B, right? And we dealt with the signs. I have here kind of the sign rule here. So we're going to do a similar thing. When you have a complex quadratic, that's when a is greater than 1, and so we're going to do similar things, but we start out after the GCF, right? So we always do GCF before all this, right? So GCF, and also set one side. And of course, before the GCF, we want to set one side equal to 0, right? Set equal to 0. So these are the two things we do first, right? And then if we see that a equals 1, then it's simple quadratic. If a is greater than 1, it's a complex quadratic. And so when it's a complex quadratic, then instead of just going straight for product of C and a sum of B, you have to actually multiply A times C together, because when you FOIL, you end up having to mix those terms together. So we're going to multiply A times C, and we're going to get what we'll call M, okay? And you can call it whatever you want. I'm just making up letters here. But then we do the similar thing with M that we did with C before. We want to find a product, find two numbers that have a product of M and a sum of B. Okay, so we still use B for the sum, but we use M for the product instead of C. Okay, so a product of M and a sum of B, and then we put them in just like we did before with the P and the Q, right? And we're going to get we'll figure out our signs as we go, but we put the P and the Q in there. But the difference is we divide by A, or we put A in the denominator. Okay, so remember, A is that first coefficient, right? The coefficient of the quadratic term, or the x squared. All right, so we divide by A on the bottom, and then we just reduce. Okay, and if we reduce to 1, then that just basically disappears, right? Anything over 1 is itself. But if we have any remaining denominators, we move those to the front of the x. So we're going to put those as coefficients for the x after we reduce. Okay. All right. And so that's the process. So it's pretty straightforward. There's a couple other ways that you may have learned, like factoring by grouping, or using the grouping method within this within this type of factoring. And there's a couple other ways, like I said, I've learned, but anyway, this is the most straightforward way I've found, and it's also very similar to what we did with simple quadratics. So I think it's easier to pick up. Okay, so complex quadratics are always a little bit challenging, but just trust me in that this is a really good method, and probably the most efficient and straightforward method of the ones that I've seen out there. And so I want to note that this still applies. Okay, so the sign of the bigger number is whatever B is. The sign of B is the sign of the bigger number, and the sign of C tells you if the signs are the same or different, right? Positive means the same, negative means different. Okay. All right, let's see some examples. Not that one. This is the one I was wanting to look at. All right, so here we have a quadratic, right? I want to set one side equal to 0. That's done. I want to check for a GCF 4, 5, 6. Whenever they're 1 apart, the GCF is going to be 1. and they don't have variables in common, right? They just each have, well, two of these have an x, but this one doesn't, so x is not a common factor. So now we see that it's a complex quadratic because a is bigger than 1, right? So a is greater than 1, so it's a complex quadratic. So then the first thing I'm going to do once I recognize that and I check for all those other things is I'm going to multiply a times c. So I'm going to do 4 times -6, and I get -24, right? So what I want to do now is I want to find product of 22 numbers that have a product of 24 that have a sum of 5. Okay, so 2 numbers that have a product of 24 that have a sum of 5. So I'm just going to make a list of 24. Make a list of factor pairs with 24. So 1 and 24, right? 2 and 12 and so forth, right? 3 and 8, 4 and 6. 5 doesn't go in, 6 goes in, and then I already see that this is on the other side of the list. So I'm going to do repeats. So that's the end of my list. Okay. So now remember here that since this is negative, or since this is negative either way, that means your signs are going to be different, right? And this tells you the sign of the bigger number. So we're going to have positives on the bigger side, and then we're going to have different signs here. Okay. So which of those have a sum of 5? -3 and +8, right? So we're going to start out the same way, almost exactly like simple quadratics. We're going to do x here, and then we have a -3 plus 8. So I'm going to put -3 plus 8. So far everything's the same, right? So here's the difference, is when a is bigger than 1, we're going to put that value in the bottom in the denominator. Okay, so that 4, this value, we're going to put in the denominator underneath these numbers that we just found. Okay, then we're going to reduce. So -3/4, that doesn't reduce, so that 4 is going to go to the front, and it's going to become 4x minus 3. Okay, so the numerator stays and the denominator goes to the front, like we saw. Okay, and then for this other one here, 8/4 reduces to 2/1, right? So you can bring the 1 over, but 1x is just x, right? So we'll just leave it. So what happens is we just end up with x plus 2. Okay, so that stayed. So after you reduce, the numerator stays, denominator goes to the front of x. All right, and that's how it's factored. So a little bit more work because we had to multiply first, and then we had to divide, right, by a and reduce fractions and things like that. But there's a lot more straightforward than some of the other ways I've seen, like I mentioned. So now we can go straight to the answer. So I'm going to get x equals +3, right? Change the sign there, and then you divide by this, so it's +3/4. Or here we're just going to get -2. Okay, and remember, if you need to show the work, then all it is add 3 and then divide by 4, right? I didn't give myself enough room there, but we would get 4x equals 3, and then we would divide by 4. Okay, and then on this side, just subtract 2, so we get x equals -2. All right, so there it is. So complex quadratics, that's how you do them.